Good day, students. On this clip, we're going to be going over the principles of mathematical induction. We're going to be going over questions, two examples. So let's go ahead and write down the title of this lesson, of this clip. So principle of mathematical induction. Okay. This is the first part of a four-part series. We're going to be going over examples 1 and 2. All right. So let's start out by writing out what the plan is for proof by induction. Okay. So the plan basically is as follows. You want to first of all show true for the base case, true for n equals, it could be 1 or whatever the foundation is. In most cases is 1. And then 2, you want to show that true for n equals k follows true for n equals k plus 1. Okay, so that's basically what the plan is. Alright, so let's take a look at example 1. Example 1, prove that oh, sorry, prove that 1 plus 2 plus 3 plus dot 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 plus n equals n times n plus 1 over 2 for all positive integers. All positive integers. So in this one, let's rewrite the statement in mathematical form. In statement form. So basically what we're trying to show here is the statement Sn, which is 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 over 2 for all positive integers. Basically means n is greater than or equal to 1. Okay, so we're going to start with the first part, which is the base case. So for the base case, we just need to show that a statement is true, show true for n equals 1. Okay, show true for n equals 1, or that S1 is true. Whichever way you want to write it, it's perfectly fine. Okay. Alright, so let's do the base case. So to get the base case, all you simply do is you substitute the first candidate in our set of allowable n's, which is 1, into both sides of the equation, and then that works out for you. Okay, so either you bring this down by plugging 1 here, the same thing. So on the left side, by plugging 1, I'll have 1. Is 1 equal to 1 times 1 plus 1 over 2? If I establish equality, that means that my base case is sound. Okay, so is 1 equal 1 times 2 over 2? Is 1 equal 2 over 2? 2 over 2 is 1, right? So is 1 equal 1? Absolutely. So our base case holds, so we may advance to the next part. Okay, if our base case fails, then that means we can't show that this is true by induction. Alright? So next thing we're going to move on to is something called the inductive step. Alright? This is comprised of 2 parts. So for the inductive step, what we're going to show here for this piece, we must show that true for n equals k follows that n equals k plus 1 is true. Alright, so that's the whole goal. Alright, so the first part of the inductive step is the inductive hypothesis. Inductive hypothesis. Alright, so for the inductive hypothesis, we're going to make an assumption. Okay, we're going to assume that assume um, Sn is true for n equals k. Okay? So what are we trying to show? What are we assuming here? We want to assume that we want to assume Sk is true. All right. So how do we write that? All you just simply do is you rewrite the original question, but instead of n, you substitute n with k. Okay. So in this case, we're going to assume that 1 plus 2 plus 3 plus dot 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 plus instead of n plus k, all right, equals instead of n times n plus 1 over 2, we're going to write equals k times k plus 1 over 2. We're going to assume that this statement is true for k greater than or equal to 1. Okay? Now, this is the inductive hypothesis. The next part is the proof, the actual proof. Okay? So for the proof, in this part, we must show our assumption, the assumption we made above. Our assumption follows that S sub k plus 1 is true. Okay, so that's what we must show. Alright, so in this part, we're going to show that S sub k plus 1 is true. Alright, so basically show S sub k plus 1 is true. Alright, so how do we do that? What we do is we're going to rewrite this statement using k plus 1. So what we'll do is we'll bring down the left side of this equation, 1 plus 2 plus 3 plus dot 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 plus k. And then we're going to write out the next term. The next term is going to be what you get when you substitute k with k plus 1. So plus k plus 1. This is the next term on the left side. On the right side, we're going to just simply substitute our k's with k plus 1. So instead of k, I'm going to have k plus 1. Let me color code this so you can understand. So instead of k, I'm going to substitute that with k plus 1. And then on the right side, instead of k plus 1, I'm going to substitute that with k plus 1 again plus 1. So in the parentheses, I'm going to put k plus 1 here. Okay? So on the left side, what I'm basically doing is substituting k with k plus 1. And on the right side, I'm finding the next term by substituting the last term with k plus 1. Okay? Over 2. Alright, if I can show the left side is equal to the right side in this equation, then I'm done. Okay? Alright, so first thing we're going to do is we're going to make a substitution. Look at my inductive hypothesis. I know that 1 plus 2 plus 3 plus dot 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 all the way to k is equal to k times k plus 1 over 2. So I can substitute this whole piece right here with k times k plus 1 over 2. So we make a substitution. We're going to have k times k plus 1 over 2 based on our inductive hypothesis plus k plus 1. And we can start simplifying the right side. This is going to be k plus 1. And then here we're going to have k plus 2 divided by 2. Alright? Okay, let's simplify it further. We need to find the LCD here, so put this over 1. And then I'll times it by 2, top and bottom. Times it by 2, top and bottom. Alright, and now we're going to have, on the left side, we're going to have k squared plus k plus, distribute the 2 to this 2 right here. So it's going to become 2k plus 2. This is over 2, and this one is over 2. On the right side, we're just going to distribute, alright? So we're going to have k squared plus 2k plus k plus 2. And then divide that by 2. Alright? Alright, so to finish it up, we just basically simplify a little bit further. So we're going to have k squared plus 3k plus 2 divided by 2. And that equals k squared plus 3k plus 2 divided by 2. Now, since the left-hand side is equal to the right-hand side, that's exactly what we want. That checks out. So we're good. So we write our concluding statement um, since S, since uh, true for n equals k follows that n equals k plus 1 is true. The original statement, the original statement is true for all positive integer values or n greater than or equal to 1. Okay, it's true for n greater than or equal to 1. Alright, so there you have it. Put your box of accomplishment. Okay, now we're gonna go into the second example, example 2. Example 2 is as follows. So for example 2, this one is going to be a question involving divisibility. So example 2, uh, prove that prove that 4 to the n minus 1 is divisible by 3. Divisible by 3, let me rewrite my 3 there, is divisible by 3 for all positive integers. Okay, so this is what we're going to prove. Now what we're going to do is we're going to start out by writing down the base case. We're going to follow this plan that we have up here. The plan is basically show true for n, and then true for n equals k equals n. The statement is true for n equals k plus 1, and that will be sufficient. Alright, so we're going to start out with the base case. The base case is always this first the first number that works in our set of numbers. Okay, so the base case in this case is going to be the first positive integer. The first positive integer is 1. Alright, so in order for me to write a base case, I need to rewrite this statement in mathematical form. So how do you rewrite divisibility in mathematical form? So in SN form, divisibility basically means that we have to show that 4 to the n minus 1 is equal to 3k, or let's not use k, let's use 3r is equal to 3r for some integer r, and n is greater than or equal to 1. Alright, so that's what we're going to show. Alright, so with that in mind, we're going to go ahead and write our base case using this mathematical equation, because it's easier to do this whole process using equations. Okay, so for base case, I'm going to show true for n equals 1. Alright, so we're going to show that S1 is true. S1 is true. So how do we show that? All we just do is plug in 1 on this side and hopefully get a multiple of 3. Alright, so it's 4 to the 1 minus 1 equals a multiple of 3, or 3r, or is it divisible by 3? 4 to the 1 minus 3 is just 4 minus 1. Is it a multiple of 3? 4 minus 1 is 3. Is 3 a multiple of 3? Absolutely, because 3 times 1 equals 3r. Equals 3, right? So in this case, we can see if I divide both sides by 3, I can conclude that in this case, r equals 1. So we can just say 3 times 1 equals 3 times 1. That shows that our base case is good. Alright, now let's move on to the next part, which is the inductive step, the two-part inductive step. So let's first of all write down inductive step, the title, inductive step. And we're going to write down what we're going to show here for the inductive step. Okay, so for the inductive step, uh, we must show we must show that true uh, true for n equals k. That's by assumption. By assumption follows that n equals k plus 1 is true. Alright, so that's the whole goal here. Alright, so let's start with the first part of the inductive step, which is the inductive uh, hypothesis. So for the inductive hypothesis, we just um, assume true, the statement is true for n equals k. Okay? We're going to assume that the statement is true for n equals k. What is that going to look like? What is s of k is true look like? What is that going to look like? So we need to rewrite assume s of k is true. So all we just do is rewrite the original problem. Instead of using n, we're going to use k for our variable. Okay, so we're going to go, we're going to assume that um, 4 to the k minus 1 equals 3r for some integer r and k greater than or equal to 1. Alright, so now we need to do the proof. The proof is we need to show that this assumption follows that n equals k plus 1 is true. Okay? So for the proof, we must show that the assumption follows that n equals k plus 1 is true. Alright, so that's what we're going to do. Alright, so in this case, we're going to show s sub k plus 1 is true. That's the goal here. So let's rewrite the s sub k plus 1 statement. So we're gonna write 4 to the k plus 1. Let me write that in blue so that you guys can see it. So instead of k, I'm going to write 4 to the k plus 1 um, minus 1 equals 3s, because r is already taken, for some integer s and k is greater than or equal to 1. Okay? So let's do this. So how do we do this? Now, if you look at this power right here, this is an exponent, so we can use a lot of exponents, the reverse. When you're multiplying exponents with the same base, you add. Now, if I want to break them apart, I'm going to write this as 4 to the k times 4 to the 1 minus 1 equals 3s. Okay? Now, I can rewrite that as 4 to the k times 4 minus 1 equals 3s. Now I need to make a substitution here with that 1. So what I'm going to do is I'm going to make myself a chart. I'm going to ask myself, what can I find a multiple of the first number 4 and a multiple of the last number 3 that add or subtract to give me the middle number, which is 1. Alright, so I'm going to write down my numbers, 4 and 3. And write down their multiples. 4 times 1, 4, 4 times 2, 8, 4 times 3, 12, 4 times 4, 16, 3, 1, 3, 3, 2, 6, 3, 3, 9, 3, 4, 12. And the target here is 1. Are any of these pairs, one from here, one from here, combinable to give you 1? Well, it turns out that even the first combination works perfectly here, 4 and 3. 4 minus 3 works to give you 1. Okay? So that's what I'm going to do here. So I'm going to write 4 to the k times 4 minus, instead of 1, I'm going to substitute it with 4 minus 3 and equals 3s. Okay? Now I'll write it as 4 to the k times 4 minus 4 plus 3 equals 3s. So if you look at the first two, I'm going to factor out 4. See, factor out 4 from here and here. So if I factor out a 4, I'm going to have 4 to the k minus 1 plus 3 equals 3s. Alright, now if you take a look at 4 to the k minus 1, and you go up to our inductive hypothesis, we already said that, assume that 4 to the k minus 1 equals 3r. So I'm going to replace 4 to the k minus 1 with 3r. Okay, so 4 times 3r, like that, plus 3 equals 3s. Okay, so this becomes 12r plus 3 equals 3s. So can I factor out a 3 from these two terms? Absolutely, right? So if I factor out a 3, I'm left with 4r plus 1 equals 3s. So if you look at this equation, if I factor out if I divide by 3, you can clearly see that s is equal to 4r plus 1. So I can rewrite it as 4r plus 1 equals s. Okay? So let's now rewrite the statement. We can say 3s is equal to 3s. So left-hand side is equal to the right-hand side, which is excellent. Concluding remarks, since true for n equals k follows that n equals k plus 1 is true. The original statement, which is that 4 to n minus 1 is divisible by 3, is true for all positive integers. Okay, so there you have it. Thanks for paying attention to this presentation. You can please subscribe to my videos for future updates, and you can find a collection of clips at mathgotserved.com. And have a nice day.